Hello again, students, and welcome to this, the 10th logic lecture of course Comp 0003. In today's lecture, we're going to continue talking about proof by induction, carrying on from where we left off. So you'll remember that last time we discussed proof by induction over the natural numbers, and that's a principle that many people learn in high school, though I don't know if it's covered in the current A-level syllabus or not. Remember that the principle of induction for natural numbers says that if you can show that something is true of 0, and that if it's true of any number k, then it is true of k plus 1, then it must be true of all numbers. Now, the justification for that is somehow quite often thought of as being, well, you can lay all the numbers out on a line. And so you can even think of this line as just being like a number of dominoes. And we show that we can knock over the first domino, which is showing p of 0, that something is true of 0. And then we know that each domino knocks over the next one. If something is true of an arbitrary natural number, then it's true of the next one. So if it's true of k, then it's true of k plus 1. So by knocking over the first domino, that causes us to knock over the second domino and therefore the third, and so eventually we knock them all over. And that's absolutely fine. It's a completely reasonable way to think about that principle. But there's a more general way of thinking about it too. Remember that we saw that we can define the natural numbers inductively. A natural number is either 0 or it is obtained from 0 by applying the successor function s one or more times. And so we show, at least the way that we'd written down induction in the previous lecture, that to show that something is true of all numbers, we show that it's true of 0, and that somehow the property is conserved under the successor function. So if a property is true of a number k, then it's true of the successor of k. And since the only ways of building natural numbers up are by applying the successor function and starting from 0, we know that the property is true no matter how we've chosen to build that natural number. Now, that means that we can kind of adapt this principle to any other structure which also has a similar inductive definition. So if we have a data type or some set of structures where we have some kind of smallest object of the structure, for example, which we might call atomic, or the smallest structures, and if we have some operations for building up larger structures from smaller ones, then what we must show if we want to see that something is true for all members of that structure is that it should be true of all the atomic structures, and that it should be preserved under the construction operations that we use to build up structures. And then we know for any structure, no matter how it's been built, the property must be true of that structure as well. Now, this principle is called perhaps appropriately structural induction. It was first popularized by a guy called Rod Burstall in the 1960s, and Rod Burstall was my PhD supervisor's PhD supervisor's PhD supervisor. So in a sense, he is my academic great-grandfather. So let's just briefly recap induction for natural numbers, and then we'll go on to look at structural induction over some common computer science structures, which are going to be, I think today we'll just see the case of lists and of trees. So let's go to the slides, and I will see you at the end. So on this slide, I've given a recursive grammar for the natural numbers in much the same way as we gave a grammar for propositional and first order logic formulas and for first order terms. So a natural number n is either the number 0 or is the successor function s applied to something which is already a natural number. So in other words, a natural number is 0 followed by 0 or more applications of the successor function. So if we want to show that some property p is true of all natural numbers, first of all we show that it's true of 0, and then secondly we assume that it holds for some arbitrary natural number k, and that's called the induction hypothesis, and then we show using this induction hypothesis that P holds for the successor of K. As an inference rule, this could be written here with where I have the two premises above the line. So P of 0 and P of K implies P of S of K, where the fact that K is arbitrary is listed here as a kind of side condition on the rule. And the conclusion is that for all n in the natural numbers, P holds of the natural number n. So you can just notice here that there are two cases for the definitions of natural numbers, and that kind of corresponds exactly to these two premises of the induction rule for the natural numbers here. So when we consider other inductively defined structures, we're going to consider it in very much the same way. So here's a grammar, or an inductive grammar, or recursive grammar for lists. So I've given it in this kind of, I've used notation from the functional programming language ML, but other languages such as Haskell have also got very similar notations for lists. So a list L is either the empty list, which is this symbol here, or it is some element concatenated onto the front of something which is already a list. So this is sometimes called cons, this double colon here. So it's either empty list or X cons L. Now X here, the type doesn't really matter that much. I mean, we could think we have lists of natural numbers, in which case X is a natural number. We could also have, for example, that X is a character, an ASCII character, in which case L is more like a string, because a string is like a list of characters. So that is this guy, the empty list, is a list, and that is the base case somehow of the definition. That's the smallest list. And then if L is a list, then so is X cons L, where X is some element. So X is like a single number or a single character or something. And so X cons L is a list, provided that L is a list. And that's somehow the step case or the recursive case of the definition or of the grammar. And also, just implicitly, nothing else is a list other than what could be constructed using these two operations, empty list and cons. So then, by analogy to natural numbers, how might we show that some property P is true of all lists? Well, first of all, we need to show that P is true of the empty list. If it's not true of the empty list, then for sure it's not true of all lists. And that's the base case of the induction over lists. Next, our induction hypothesis is P holds of X's for some where X's is an arbitrary list. That's the induction hypothesis. I'll just remark that it's quite common to write variables for lists as like two letters with the second one being S, X's. And that's kind of just to remind us that it is a list. I'll also sometimes just write L. And then we show that for any arbitrary element X, P holds of X cons X's. So in other words, the kind of step case of the induction is that if P holds of a list, then it also holds when you add an element onto the front of the list. So again, we can write this as an inference rule with two premises, one premise for each of the two construction operations for lists. The first premise, the base case, is that P holds of the empty list. The second is that for all elements X, if we have P of the list X's, then P holds for X cons X's. And then where X's is arbitrary, and this should actually say that X is kind of arbitrary as well. And the conclusion is that for the P holds of all lists L. So now we're going to get some practice reasoning by structural induction on lists. And for this, I'm first going to define a few common recursive functions on lists. They are recursive in the sense that the result of the functions for a larger list made by a cons operation is defined in terms of the result of the function for the smaller list, which is its tail. So the length len of the empty list is 0. And the length len of X cons X's, so a compound list, is 1 plus the length of X's. I've labeled these equations here as 1 and 2. next function is going to be the append of two lists. So it's supposed to take two lists and return the result of appending the second one onto the tail of the first. So I'm writing it in fix, and I'm defining it by recursion on the first argument, quite similar to when we defined addition on the natural numbers. So if I append y's to the empty list, so I have empty list at y's, then that is just the list y's itself, so it has no effect. And if I take a non-empty list, x cons x's, and I append that to y's, well, I can assume recursively that I already have the result of x's at y's, and so I just take that result and I cons x onto the front. So hopefully you can see that this really does just do the thing of taking the second list and joining it onto the first one. And finally, a function rev for reversing a list. Now that's going to use the append function that we've seen already. So the reverse of the empty list is just the empty list itself. And if I want to reverse a non-empty list, x cons x's, well, first of all, I'm going to reverse the tail of the list, so I'm going to reverse x's, and then I'm going to append the singleton list consisting of just the element x. So this is written as x cons empty list. That is, if you like, a one element list containing only the element x. So I reverse the tail, and then I add on to the end the element x and the empty list. Okay, so hopefully I'm going to do like a little bit of window manipulation here, so I can keep these equations up while we go on and look at our examples. Almost worked. Okay, good enough. So yeah, I'm going to keep the definitions of these functions on the left hand side here, and I'm going to carry on working on the right hand pane. So here's our first list induction example. For all lists x's and y's, the length of the list x's at y's, so their append, is the sum of the lengths, len x's plus len y's. And hopefully you can see that that's true. I mean, or it should be true. If you join two lists together, then the length of that should just be the sum of the lengths of the two lists that you've joined. So I'm going to prove this by induction on lists. I do have a choice about whether I want to do induction on the list x's or the list y's, and I'm going to choose to do induction on the list x's because I'm noticing that the function at is defined by induction on its left-hand argument, and that means that, for example, our base case will be when x's is the empty list, and I know that I have a case where the left-hand argument of append is the empty list, which is in our equation 3 here. So it's more of a sensible choice in this case. So we're going to go by structural induction on x's, and remember that when we strip the quantified, the variable that we do induction off of the lemma statement, then the y's is still universally quantified. So our property of lists, P of L, is for all y's, len L at y's equals len L plus len y's. That's just by taking x's equals L in this equation here and stripping the for all x's quantifier off the front. So in the base case, we have to show that P holds of the empty list. Now we substitute the empty list in for L in P here, and this gives us exactly that we have to show the length of empty list append y's is the length of the empty list plus the len of y's. Now that's pretty easy using the equations 1 and 3 on the left hand side. You can see that the length of the empty list is just 0, so the right hand side is just len y's, and on the other hand, empty list appended to y's is just y's itself, so the left hand side is also len y's. So that's easy. Now the induction hypothesis, I just have to, so I'm going to take the variable z's as my arbitrary list that I'm going to assume is true in the inductive case. So I'm going to assume that P holds of a list z's, which is exactly this statement here, and I have to show that is then true if I cons an element onto z's. So in the step case, I have to show something for all y's, so I'll just let y's be any list. And I will take an extended list, z cons z's. So z is an element, and I'm consing it onto the front of z. So given p of z's, which is this induction hypothesis here, I have to show p z cons z's. And that is exactly this property here, just by substituting z cons z's into this guy here. So that'll take a bit more time, so I'm going to continue this on the next slide. So here's what we have to show in the step case of the induction. The length of z cons z's at y's equals the length of z cons z's plus the length of y's. Well, okay, let's start from the left-hand side and work our way over to the right-hand side. This is quite a good way. We've got some equations to use here, and we've got an induction hypothesis. So I guess the first thing we can that we can look at here, we could try to rewrite using the definition of len, but we can't, because this list is neither the empty list and it's not the cons of something plus a list. It's not element cons list. It's actually at the top level, it's an append of two lists. So it makes sense to actually rewrite innermost first using the definition of append. And by equation 4, z cons z's at y's is the same as z cons z's at y's. So that's just by rewriting according to equation 4. And then now we do have something in the form z cons list, this z's at y's. So we can apply equation 2 to get that the length of this guy is 1 plus the length of z's at y's. Now, by the induction hypothesis, the length of z's at y's is exactly length of z's plus the length of y's. And then by applying equation 2 again, this is equal to the length of z cons z's plus len y's. So here I've used the equation 2 again, but I've somehow applied it in the other direction that I applied it the first time. And so this, we showed that the left-hand side and right-hand side are equal. We've used the definitional equations and the induction hypothesis. So we've shown the base case, we've made our inductive assumption for z's, and we've shown that the property is true for z cons z's. So this completes the induction, and the conclusion is what we were trying to show at the beginning, that for all lists x's and y's, the length of their append is the sum of the lengths of those two lists. So we're done. Okay, so here is our second example. And in some ways, I think this might even be a bit simpler than the first. For all lists x's, the length of rev of x's is the length of x's. So in other words, if you reverse a list, then you don't change its length. And it seems quite clear that that is or should be a true property. We're going to proceed by structural induction on the list x's. We don't have a choice about which variable to use here, so that's okay. In the base case, we have to show that the length of the reverse of the empty list is the length of the empty list. Well, this is easy. The length of the empty list is 0, and the reverse of the empty list is the empty list as well. So in fact, this can be shown just by one application of equation number 5. You don't even have to use the fact that the length of the empty list is 0. So that's easy. Next, I'm going to assume the property for some arbitrary list, which in this case I'm calling y's. So I'm assuming that length of rev of y's is equal to the len of y's. And then in the step case, I'm going to show that the property holds when I cons an element onto the front of this of this list y's. So we have to show that the length of rev of y cons y's is equal to the len of y cons y's. And again, I'm going to start by just going from the left-hand side and trying to derive the right-hand side using the definitional equations and the induction hypothesis. So, by definition, I can rewrite the definition of rev of y cons y's using equation number 6 over here. So by definition, rev of y cons y's is rev of y's appended with y cons empty list. And that's just by equation 6. And now, remember that we just showed a lemma that says the length of a list which is of an append of two lists is the sum of the lengths of those lists. So by the lemma we just showed in the last two slides, that is equal to the length of rev of y's and the length of y cons empty list. Now by induction hypothesis, oh no, sorry, I could have used it straight away, but I guess I haven't done it yet. So first of all, I'm going to simplify the right-hand summand by noticing that the length of y cons empty list is 1 plus the length of the empty list by equation 2, and which is equal to 1 plus 0, which is equal to 1 by applying the length of the empty list is 0. So this this right-hand summand here becomes just 1, and by induction hypothesis, the left-hand summand becomes len of y's. So we have len of y's plus 1 by induction hypothesis. And then finally, by applying equation 2 again, this is equal to the length of y cons y's. So we're done. And you can find some more examples that ask you to try structural induction by lists on the exercise sheets on the middle page. Okay, let's go on and look at another structure. And here I'm going to consider the case of binary trees. I mean, in some sense, trees are quite similar to lists, except that instead of being one-dimensional, they're somehow two-dimensional, or they branch. So a binary tree can be given inductively by this grammar. A tree T is either a leaf, which I'm writing using just this LF, or it is a branch made up of some data. So I'm imagining, again, some data being stored in the trees, just as they were for lists. So X might be a number, or it might be a character, or something else. And you have a left-hand tree and a right-hand tree, which are somehow the child trees of that branch. So just to go over it again, a leaf is a tree, and that is somehow the base case of the definition. Those are the atomic trees, if you want to think of it that way. And then if we already have two trees, T1 and T2, then so is branch of X, T1 and T2, where X is some kind of data. So that means that, for example, branch of X and leaf is a tree, for example, and as before, nothing else is a tree. Okay, so now suppose that I want to prove some property P about all trees. Well, again, our induction scheme has to reflect this definition and say, well, again, there's two ways of building trees. The only thing which is really different from the case of lists is that rather than a list having being constructed from an element and another list, in a non-empty tree is constructed from a piece of data and two trees. So we're going to have to reflect that in our induction principle. So to show that P holds of all trees, first of all, we have to show that it holds of a leaf, LF, that's the base case of the induction here. As my induction hypothesis, because branches are built from two subtrees and not just one tail list or one preceding number, I'm going to assume that P holds for two trees, T1 and T2, and you can think of these are going to be the left and right subtrees of a branch. So assuming this, which is my induction hypothesis, I have to show that P holds for any branch constructed by from X, T1 and T2. So in other words, if P holds of the left subtree and the right subtree, and I put a piece of data in between them, then P is still true. And that's the step case. So here's the inference rule. The base case, again, there's two cases of the definition of a tree, and that gives us these two premises. So we have to show that P holds of a leaf, and that if it holds for the left and the left and right subtrees of a branch that it holds for the branch itself. So if it holds for T1 and T2, then it holds of a branch with X, data X, and left subtree T1 and right subtree T2. So here X, T1, and T2 are all arbitrary. And the conclusion is that T is true for all trees. Now, just as in the case of lists, I think it's good to get a little bit of practice with structural induction on trees. And so I'm going to define a couple of functions by recursion on trees. First of all, a pretty simple size function. So the size of a leaf is 0, and the size of a branch with X and left subtree T1 and right subtree T2 is 1 plus the sum of the sizes of the two subtrees. 1 plus size T1 plus size T2. This isn't the only possible definition of the size of a tree, but but it's a pretty good one. It's it's quite commonly used. And here is a function refla for reflecting a tree somehow along its reflecting its left and right subtrees, reflecting it from left to right. So the reflection of a leaf is just that leaf itself. And if I want to reflect a branch with X, T1, and T2, then I'm going to reflect the two subtrees and put the reflection of the right subtree on the left and the reflection of the left subtree on the right. So in other words, if I reflect a branch with X, T1, and T2, then that is a branch with X because the data doesn't change, and the left subtree is the reflection of the right subtree, reflect T2, and the right subtree is the reflection of the left subtree, reflect T1. Now I'm just going to do my trick with the windows here again. Oh, again, doesn't, almost works, not quite. There we go. And now just to finish off, I'd like us to do a quick example. I'm going to keep the definitions of the functions on the right hand side just to be clear. And I'm going to show a pretty simple lemma. Actually, it doesn't even use size. I think it's because I've got some more examples in the next lecture that probably do use size. So whatever, we're only going to need the definition of reflect for this lemma probably. So for all trees T, reflect of reflective T equals T. So if you reflect a tree twice, you just get that same tree back again. So the proof is going to be by structural induction on trees. And the property to be proven is that reflect of the tree is equal to the tree. So in the base case, we are required to prove, by the way, I often use this abbreviation RTP, that is for required to prove. So it's just a handy notation for keeping track of what it is that we have to prove at each stage. And so it's a handy thing to use in proofs. So we have to prove that reflect of a leaf is equal to a leaf. And that is easy to do just by two applications of equation number 9 here. So sorry about the typo. I don't know why it says 7, should say 9. Now, the induction hypothesis is that the property holds for two subtrees, T1 and T2. So we'll assume that the property holds of T1 and that it holds of T2. Now we have to show, as our step case, that it holds from a branch constructed with some data and left subtree T1, right subtree T2. So we have to show that reflect of a branch with X, T1, and T2 is equal to that branch itself, branch of X, T1, T2. So let's start with the left-hand side, which is this guy. Just by applying equation number 10, we get that this is immediately equal to, we're actually going to rewrite with the inner term here. So we have reflect applied to a branch. That's all inside another reflect, but we're going to kind of ignore that for now. So we'll use equation 10 to write reflect of branch X, T1, T2 is exactly this guy here. So we've just replaced it. And then by applying the equation again, we have reflect applied to another branch. So we get branch of X, reflect T1, reflect T2. And then by the induction hypothesis, that is exactly equal to branch with x and t1, t2. And that's exactly what we wanted to show in the step case. So this finishes the induction, and the conclusion is that for all trees t, reflect t equals t. And I think that will do quite nicely for one day. Thank you for your attention, assuming that you paid any. And in the next lecture, we'll get a bit more practice with structural induction, and I'll also begin to talk about some alternative ways of doing induction over the natural numbers and other structures. So until next time, take care.